Hello, how's it going? God lives and loves us. Talk about chemical reactivity here for a minute. So there's a great resource in the CSB, the chemicalsafetyboard.gov website that you see there, improving reactive hazard management. It highlights over 100 safety incidents with reactive chemicals, and highlights incompatibilities, out-of-place chemical concentrations, runaway reactions, and process upsets that resulted in severe incidents. That's a resource there. It's a great one. Here we'll also talk about Gibbs Free Energy for a minute as far as identifying spontaneous reactions. Highlight the chemical compatibility matrix. This is binary kind of interactions between chemical A and chemical B. Also talk about calorimetry for a second. That's basically a well insulated container that you can result in you put chemicals in there, you can heat it up and see how much energy is released. And then we'll talk a little bit about kinetics. So reactive chemical groups include azides, sodium azide, those azide chemicals are very sensitive, and they're used for in primers and small arms ammunition, as well as some of the diazo compounds. Of course, nitro compounds are used in smokeless powder that make it so that the oxidizer is tagged right along with the fuel, the carbon. And then there's others like peroxides and chlorates that are also rich in oxygen and can be reactive. Pyrophoric, those are burn when contact with air. Sometimes with fine metal will burn, and other chemicals. Of course, sodium and lithium and potassium, those chemicals will react with water. Oxidizers like nitric acid and peroxide. There's self-reactive or autocatalytic nitrocellulose I mentioned, or gunpowder, smokeless powder. That, it will degrade over time and generates nitric acid and releases heat and generates more and more breakdown chemicals that can, eventually it heats itself to where it burns, and that's autocatalytic. And then incompatible materials that can be mixed together. And Appendix D in Kral and Luvar's safety manual, this one here highlights additional reactive chemicals. It's a good resource. And the this chemical reactivity worksheet provided by the government initially put that together with the EPA, and AICHE has ownership right now, and you can get it for free. It's best with Windows machines, but you can download and install right there. There's a little link. And then there's also this Breatheric's Handbook of Reactive Chemical Hazards. This is version 6. It's $150 used. The newest version's $550. It's the 8th edition, but that's a good, well referenced book on identifying hazards for different chemicals and gases, and great resource. sorry, apologize. Moving you around on the screen here. So that compatibility I mentioned there at the end is important. It's very rare that you'd have just a single chemical in a process. And when you mix chemicals or have chemicals in contact with one another, either that's designed or not designed, sometimes with perhaps lubricants, and you're pumping something through a pipe and it comes in contact with the lubricant, it can react. And there's this binary chemical compatibility matrix where you have across the top chemical 1, 2, 3, or 4. It's an identifier, and then the row similarly. And you can indicate whether or not chemicals are compatible. They can be self-reactive, incompatible, compatible, or a caution. And there's different ways to determine if the chemicals are compatible with one another. There's, of course, you can test them. We'll talk about that with, calorimetry kind of test methods. The SDSs, safety data sheets, can indicate what a chemical might not be compatible with. I mentioned just that Breathrix handbook, as well as the AACHE chemical reactivity worksheet. And then let's talk about, thermodynamics, the Gibbs Free Energy. If you mix two chemicals, for instance, we'll just do a simple one, methane and oxygen. So, where are we? Right here. So, methane and oxygen, of course, can combust to CO2 and water, and their products are at a lower free energy than the reactants. And Gibbs Free Energy, you'll learn more about this in your thermodynamics class. H is enthalpy, S is entropy, T is temperature. And the Gibbs Free Energy is defined by the difference between the enthalpy and the product of temperature and entropy. And if you have a reaction coordinate of chemicals in a state A versus going to state B, if that grouping or chemical setup has a lower free energy for state B, then that reaction is spontaneous. However, it may not be very fast. So thermodynamics tells us about the states of chemicals, however, it doesn't say anything about the rate of reaction. And so you can look up on Dipper or other database what the Gibbs free energy of formation is for methane and oxygen. And similarly with the heat of reaction for Gibbs free energy, pure components have a Gibbs free energy of 0. Typically. And so you have methane and CO2 and water there. And notice that the products minus the reaction sum is minus 818, meaning that the methane will react with oxygen. Here's another example with acetic anhydride and sodium hydroxide. And you can use that Gibbs free energy to say, are they compatible or not? And here the Gibbs free energy indicates that they will react to form, give off heat. You could calculate the heat of reaction for that. And looks like from that reaction there that the net total number of moles, similar to methane combustion with oxygen, is the same for the products and reactants. So I failed to mention earlier that you can also use AI tools, and I invite you to do that, to look up ChatGPT or Gemini or other AI tool generate a chemical compatibility matrix. And now they're large language models, so sometimes the accuracy isn't very good, but it can help you get started, and then you'd want to verify the information there. So now if we switch gears and talk about kinetics, you have all learned about the Arrhenius equation, where you can indicate the reaction constant K is proportional to a pre-exponential factor A, and the exponential of the activation energy, EA, divided by the gas constant times the temperature. And that reaction constant, it's I don't necessarily like that reaction constant name because it can change with temperature, so it's not that constant. But that is K there. And typically for reactions, rates depend on the quantity of the reactants. And those are orders of reaction. They can be 0, so they're not dependent on the reactant concentration. They can also depend on the product concentration sometimes. If there's a interaction there between the products and reactants. However, that's not very common. Typically, it's just the reactant. As you see, there's the partial pressure of methane and the partial pressure of oxygen. That determines the rate of reaction with methane there. And when it reacts, of course, it gives off heat. And that's your heat of reaction. And that reaction rate is a function of temperature as well. So there's different methods to be able to determine kinetic parameters. I've shown a few here with DSC and ARC, accelerating rate calorimetry, and others. You heat it up and gradually see how much reacts at different temperatures. And I'm not going to go into the details of each of those different calorimeters, but they're frequently used, and you can get kinetic data from them, as well as thermodynamic data of heats of reaction and so forth. Now I'd just like to finish with giving you a brief discussion of highlighting the combustion of fuel inside of a closed container. We talked about this in class a little bit with the 20-liter sphere, where you can disperse fuel or dust inside of a sphere and then ignite them and measure the pressure. And we talked about the KST value, and the KST value, that's typically for dust, and that is the change in pressure with respect to time. That's a maximum times the volume of where that pressure was measured to the 1/3 power. And kg is for gases. And you'd have a plot similar to that, and this dp dt max is right there. So we could look at that for methane combustion. And so you have methane and 2 moles of oxygen for a total of 3 moles reacting to carbon dioxide and 2 moles of water for also a total of 3 moles. And if we do energy and material balance on that, the total change of moles is 0. And we can also do an energy balance there, where we have the energy change of our control volume with respect to time. That's this leftmost, or this is our accumulation term. And we have a sum of the inlets and the outlets the difference between them in terms of energy brought in and energy leaving. In this case, it's sealed, so it's 0. And we can say it's adiabatic, so the Q for our control volume is 0, and there's not any shaft work. So that's this general energy balance you'll see in thermodynamics, and you've seen pieces of it in fluids. And so yeah, in this case, we don't have any ins or outs, but we just have a generation term where methane is reacting. And we can say that reaction constant is, in this case, maybe a constant. And we say that temperature doesn't really change. We can just say it reacts at a given moles per second per volume. And then we have our product reactant reaction of K times our volume, and the amount of heat for each mole per se is a given quantity or energy quantity in joules. And we can get a change in the energy. And why would we want that? Well, we could understand how the temperature changes as well as the pressure from that. And so that's kind of what I go through here. And you can see, right, let's see if I can get this for you. This dNu d time with respect to T, or the change of the total internal energy of the control volume with respect to T, that's this term I'm underlining. You can differentiate it by parts, and dN dt is 0 there, so that means N, you can have total moles of N, and then get du dt, and du dt, U is the internal energy, and it's the heat capacity with constant volume, times the difference in the temperatures, or the change of temperature with respect to time. And then you can get an equation that's like this, and you can get a change in temperature with respect to time. And if you have a change in temperature with respect to time here that I'm putting in that little rectangle, you can also get pressure with respect to time. So you can see that if I have test data that gives me this pressure with respect to time, I can get some of these parameters. Heat of reaction, this K value, and start to estimate some of those. You can use similar models or energy balances to get maybe what would happen in a processing scenario about how would the pressure exceed the pressure rating for the vessel or the room per se, and maybe I should vent it to allow gases to vent out, put a pressure relieving valve or maybe a blowout panel, and you can do this similar kind of mass and energy balances. In this case, now you have moles of gas out or mass out, and you can get that from gas flow out of an orifice. And in this case, it's maybe frictionless as a first estimate, and you can get how that pressure as a function of time is what would happen to your vessel. That's a way that you can estimate violence from a chemical reaction. Over here is some more details. I went a little more into like, how does the vent actually move out of the way? It's not just instantaneously that you get an opening event, but typically there's like, you move from closed to open. And you can use physics where pressure pushes on the panel and opens it, and you can calculate accelerations and velocities of the panel, or you can just estimate it with an S-curve kind of a thing where that vent opens gradually. Not going to be tested on this in terms of calculating a venting rate, but I wanted you to see how you can use energy balances to get what kind of pressures you could expect inside of a vessel. I wish you the best, and have a great one.